The following is a conversation with Jimmy Tomaselli, PhD student at the Gravitational and Astroparticle Physics Amsterdam Center of Research known as GRAPPA. Jimmy is in his final year of PhD and is now writing his thesis on black holes superradiance. Recently, he got offered a postdoc position at the Institute of Advanced Study in Princeton. I hope you will enjoy this conversation, and this is Back to the Stone Age. Jimmy, is mathematics invented or discovered?
So I would say it's discovered. That's my view. Why would you say it's invented?
Because we invent the axioms upon which we build the mathematical structure or a mathematical theory.
Okay, I would rather say we choose what to study in mathematics,
Okay.
but the consequences are not made up. The consequences are discovered. And even in some sense, the axioms, the interesting ones to study, are not made up. It's not just something that depends on the mathematician. Now, to be honest, yeah, it is a bit mysterious that the things that we find interesting to study in mathematics then turn out to be useful in completely different areas. That is indeed surprising, but I would say mathematics is discovered. If you talk with an extraterrestrial intelligent being about mathematics, you will agree on what's true and what's false.
Don't you think that the assumptions, so the axioms that we start from, are okay? The assumptions that we start from, the axioms are dependent on what is intuitive for us, right?
In some sense, yes, there is some notion of intuition in the set of axioms we use, but we also refine the axioms such that we get an interesting mathematical structure from them. So it's not just pure intuition. So, for example, the famous axiom of choice has seemingly paradoxical and completely counterintuitive implications, such as the Banach-Tarski paradox.
What is it?
Banach-Tarski paradox says that you can take a sphere, a ball, so a set of points with a like radius less than a certain fixed amount, and you can do operations on these points like rotations, translations in the space, rearrange their positions, and end up with two balls, each of them with the same size as the original one. So like duplicating the original ball. And
Okay.
you can do this by only dividing up the pieces in 5 different sets.
Okay.
You can do operations like rotations, translation, and you end up with 2 different balls. This is something that is a consequence of the axiom of choice, which we assume is true. I wouldn't say this is very intuitive.
All right. Okay. I see your point.
It's just that it leads to a rich mathematical structure.
Okay. Then what is the difference between maths and physics? And I want you to give you the image, or at least an image that I have been thinking about from Roger Penrose, sort of the impossible triangle of Roger Penrose, where it says that mathematics is a superset. The mathematical world is a superset of the physical world, because within mathematics we can describe the physical world, but also things which are really not in the physical world. In the physical world is a superset of what it says that what he calls the Platonic world, which is basically the mind space, what is consciousness, what we can think of, and he says that what we can think of is a superset of mathematics again. What do you think of this view? And then what is the difference between maths and physics?
Okay, so first of all, I'm not too familiar with this view by Penrose. So to give you a detailed opinion, I probably have to think a bit about it. So, I mean, if each of these is a superset of the next thing, then they're all the same. right?
Yes, that's why it is called impossible, because it is sort of paradoxical, because you
No, I mean there can be if there's a closed chain of supersets relation, that it means that all the sets are identical. No.
But the thing is, can we find the elements in one set which are not elements of the other
I
set?
see. I see.
For example, I can think of as of now, I can think of emotions. So love, just very trivial example. Love is not described mathematically, I believe. So it is not a member of the mathematical world. It is a member of the mindscape.
I see. Look, I don't know.
Okay.
I do not tend to think about these concepts philosophically this way. So if you ask me what's the difference between math and physics, I would tend to think operationally. So for example, for physics, we need to do experiments to find out how the world behaves. For mathematics, it's just an abstract process.
Okay.
What we can think in our mind, I do not consider that as a separate philosophical entity. It's just a set of biological processes that create something we perceive as a different word, but it just exists in our reality, in my opinion. There's nothing magical about it.
Okay. We will definitely come to that later. I want to ask you, we have in our sort of physical reality, there seem to be some paradoxes, which sometimes might be related to language.
For example?
For example, uh, if I say this statement
Yeah, okay.
is false, well, I cannot find a sort of logical. I cannot evaluate it logically such that it does not lead to a consistency. So some of them are related to, I'd say, yeah, logic, are related to language. Some of them are related to what is the common intuition. For example, Zeno's paradox. You can say never reach a place because before reaching that place you have to have traveled half the distance.
Yes.
After distance all motion is impossible. This kind of stuff. Are paradoxes intrinsic to our way of perceiving reality, our way of communicating and describing it, or are they intrinsic to reality itself?
I think they do not really exist. So the example you made with this sentence is false, I wouldn't call that a paradox. It's just that that sentence is neither true or false within the
Okay.
usual scheme of
Okay.
logic. Like even like we know that there are some statements that are neither true or false.
Okay.
There's nothing paradoxical about it.
Okay.
No?
Okay. It defies the law of excluded middle. How can we, I'll say, then how does a statement that has no,
I mean, we know even in mathematics there are some statements that are neither true or false in a given set of axioms.
okay,
You can prove that you cannot prove
yeah,
that they are true or false.
okay.
So that's first
So that's, you say,
Gödel's theorem.
yeah, you say it is simply built, it's not a paradox, it is simply built into the structure of mathematics.
Yes,
Okay,
on logic, yes.
logic, okay.
I wouldn't say that's a paradox. Then if you ask about paradoxes in the physical reality,
Mhm.
this is not obvious, but I tend to think they do not really exist. So if like because the word is so well described by mathematics, it would be very weird for me that the mathematics that describes the words contains internal paradoxes. I do not. I tend to think that is not what actually happens, but this is not necessarily the mainstream view. I think
Okay.
that's just my personal view.
Okay, and then you just mentioned the mathematics describes so well our physical reality, and there is probably not an answer for this. There is probably not an explanation. But what is to you the reason of the unreasonable effectiveness of maths? How can it be that by positing a bunch of axioms and then building onto it further concepts, we can get to describe almost everything that we see around us and also that we don't see.
It's very hard to elaborate an answer to this. I read the paper by Wigner some time ago. I felt like I didn't fully understand um, many of the things he meant. So to me, it's more that I cannot find an alternative. So the only thing I know that is capable, in principle, of describing the physical reality is the logical structure of mathematics. I do not know anything else. So in this sense, I do not see how mathematics could not be effective.
Okay.
That being said, maybe the most surprising thing is that what we choose to study, as I was saying before, in mathematics, maybe because it's interesting or beautiful or leads to rich mathematical structures or theorems, often is the same thing or the same concepts turn out to be very useful in physics. That's quite surprising to me.
How do you think, I agree, how do you think, or let's say, how do you view this revolution in string theory, which has happened in the past, in the recent years, where at least I've heard physicists speaking about it, and it seems one of the first cases where a branch of physics leads to development in mathematics, leads to the deployment of new tools.
Is it the first time though? Now I cannot think of a clear example. I don't think that's the first.
Or maybe they say one of the most evident or eccentric cases of such a deployment.
But I'm quite sure it happened in the past that physics needed some advances in mathematics, and that pushed mathematicians to study certain things.
Okay, no, wait. What I mean is more like that some things, or let's put it this way, very
Like
brutally.
calculus, for example.
Yes, but very, I mean strict mathematical tools which are born out of physics and find application in more purely in a more pure mathematical work.
Yeah.
That is at least how I interpreted it. Maybe I didn't misunderstood. I think it was Brian Greene.
You know, I think it's just related to what we said earlier, that interesting mathematical concepts turn out to be useful in physics. If we study physics, we find that we need some mathematical concepts. Chances are they are interesting mathematically per se as well.
Okay.
So to me, it's just the other face of the coin.
Sure. All right.
Of the medal. How do you say that?
Mhm.
Yeah, of what we said earlier. So I don't find that surprising per se. To me, it's just the same thing as before.
Okay.
And
Alright.
also, I don't think string theory is particularly special in this.
Okay.
It happened in the past.
What is your opinion of string theory? Is it
Opinion?
yeah,
What
is it
sense?
I mean, is it okay, if you had to say whether or not, like if you had to bet money, whether or not all of your money on whether or not string theory could actually be a theory of everything or could explain within our universe the unification of quantum mechanics and general relativity, would you say it could be or it can never be?
I would say yes.
Okay, why?
It's very compelling theoretically. It's very compelling that it's, the incorporation of gravity within string theory is inevitable, and it has some mathematical properties that seem too good to be just an accident.
Okay.
So if you ask me, and also the other contenders for uh, theories of everything, or anyway beyond the framework of quantum field theory, to me don't sound as compelling as string theory.
Okay.
But what I'm saying is irrelevant. We just need
Sure.
to study this thing.
Sure. What about the extra dimensions? However, how can you possibly ever get to make a prediction from string theory and sort of be able to test it, or let's say make a prediction that uniquely would certify the theory to be true, because it predicts a dimension we don't see. How could we test, for example, for these extra dimensions?
So you can, for example, I mean, some particle physicists have tried to find extra dimensions at CERN. You can, for example, excite some modes that live in the extra dimension. So if you see some energy disappearing from the 4 dimensions, we know that maybe went into the extra dimension, we don't see it, something like that. So some predictions are like testable, like predictions of string theory are in principle testable, but not so much in practice. But I'm not worried about testing string theory experimentally. I think nobody really is.
Okay, why not?
Just because it's relevant for a regime of physics that is just not accessible to us.
Okay.
It's just accessible theoretically.
Then why the need of finding a theory of everything, or why the need of reconciling quantum mechanics and general relativity if we know that they are just way beyond our capacity?
It's just theoretical need.
Okay.
It's just that it's unsatisfactory to not have a unified theory.
Okay. What are in principles these theories of everything? Because um, if I think about someone speaking about the theory of everything, then I say, okay, would this theory predict why did I born? Why did I came to the world? Or what is meant with theory of
No,
everything?
so recently I read a book by Weinberg. It's called Dreams of a Final Theory.
Okay.
And it has a very nice explanation of, or definition of theory of everything. And it also explains why the theory of everything is not supposed to predict why you were born or stuff like that. So the explanation for what is a theory of everything is, the definition, is that if you try to explain properties of reality, for example, the white color of a piece of chalk, that's the example that Weinberg uses. Then, I mean, the white color is due to the light it absorbs and reflects, right? But why does it absorb those wavelengths and not others? And then you have to explain the atomic structure and what are the energies involved. And you ask, okay, but why are these the energies of the atom and not others? And then you have to involve the, masses and interaction strengths for the various particles and so on. And you're up to the standard model. And if you ask different questions about physical reality and you follow all these arrows, you end up roughly at the same point. So it seems like whatever question you ask about the universe, you can follow this chain of implications, and all these arrows seem to converge at the same point. So this suggests that there is one explanation to which all the others converge to.
Okay.
No, we don't have yet this unified theory. That's what a theory of everything would be, like the end of all the chain of explanations or implications
Okay.
about properties of physical reality.
Is this
And also let me complete. It wouldn't predict why you were born,
Okay.
because that's not a property of the universe. That's about the initial conditions. That's about a so-called accident.
Okay.
So, in physics, you need 2 things. One is the equation you need to solve, and the other is the initial conditions.
Okay.
Okay, why you were born depends on the initial conditions.
Okay. All right. Well, end of my question. Okay, all right. Do you think it is ever, in principle, ever achievable, a theory of everything that gets to the final chain, final point?
I don't see why not.
Okay,
Or no, sorry, I should say, I think I don't see an obvious obstacle in reaching it.
okay.
I think it's conceivable that there is indeed a theory of everything in the sense I described.
Why wouldn't it be the case? Why couldn't it be the case um, that we simply get to find more and more questions to reply, to try to
It
answer?
could be, but if you look at this chain of arrows I was describing earlier, and again, this is a picture by Weinberg, it's not something I'm thinking about now.
Sure.
It looks like they all converge to the same point. It looks like there is indeed some unified explanations for the things we see and experience. So it could be that that it could be that you find more and more questions, but that's not what seems to be hinted by what we know so far. It looks like the deeper you look, the fewer are the concepts you need to explain what's going on.
What does this tell you about the reality? About
In what sense?
is it ironic or is it logic, intuitive for you, or surprising? That given all the amount of information that we can describe about the universe, everything can be summarized in a way by, as you said, fewer and fewer concepts. Does this, to you, point to sort of a grand design? Maybe with or without a grand designer, simply some big unified schema where everything within which everything makes sense, or is it
I don't really get the point of the phrase grand design, so I'm not gonna use that.
well, okay? If you have a
They,
theory of everything,
yes.
isn't doesn't this look like sort of as a big unified framework where at the sort of at the top, or let's say by zooming out, you can see everything described, as you said, with very few concepts. And as you keep on zooming in very specific different reasons, different parts, different areas, you see a rising structure and richness for the different type of explanation that you can have in the different areas of this framework.
So I think about a possible theory of everything as just the rules of our universe, in the same way as made up universes. Like, do you know the game of life? Where you have an infinite grid and
Yeah.
you define rules for when the cells are alive or dead.
Yeah.
You know, that's a universe with the rules.
Okay.
I tend to think about a possible theory of everything for our universe in a similar way. So it's just the rules of what's going on.
Okay.
To me, it's completely plausible that that's what's going on. I wouldn't call that a grand design.
Okay. What if gravity and quantum mechanics could never be reconciled together?
But we know they can.
Okay.
We have some examples where they can.
Okay. But we cannot test the validity of the many of these theories that they do.
Exactly, yes. Quantum gravity is out of reach experimentally, according to most scientists.
Okay. So you say the problem of okay. So basically, what you're if I understand correctly, what you're trying to say is the problem of quantum gravity is more engineering than theoretical, because theoretical we have many nice theories. If we were infinitely developed engineering wise, we would be able to test them and see.
So first of all, I want to say something about quantum gravity. there is something that always bugs me, and that is that, I mean, maybe due to historical legacy, the phrase quantum gravity and the problem of quantum gravity is often explained in a bit misleading way. So general relativity makes perfect sense as a quantum theory, as an effective field theory.
Okay.
So there's no problem in quantizing gravity at low energies. You can make predictions, you can compute the quantum corrections to the Newtonian potential, to the gravitational attraction. It's completely fine. It just works like all other effective field theories that we have. The only problem is that effective field theory doesn't have ultraviolet completion within quantum field theory.
Okay. What does it mean?
It means that its predictions start to do not make sense anymore at high energies.
Okay.
So it has a limited range of applicability.
Okay.
And if you think that is a very big problem, then you should consider that all our other theories of quantum fields, like the standard model, are also expected to be effective field theories. We totally expect that at some high energy, new degrees of freedom, like new particles, will be discovered or can exist, right? Which would make the standard model an effective field theory. So conceptually, it's not very different.
Okay.
The real problem with quantum gravity is that general relativity is not completable in the ultraviolet within quantum field theory, as far as we know.
Okay.
Okay. So most people have taken the approach of changing the framework, like switching to string theory or something else, to incorporate quantum theory of gravity. And I forgot the original question.
No, it's well, I mean, you were talking about you were saying whether if quantum gravity is even a thing. I said, what if they could not be reconciled?
No, I mean they can be reconciled. We have some examples where quantum gravity is solved in some sense, some toy models. We know that those works. We just don't know what is actually the right model for our reality.
Okay.
Well, we know in some cases it works.
Okay.
And
but isn't it a sort of a big, not a big problem, but okay, theoretically, of course, isn't it because practically we are very much fine, but isn't it theoretically a big problem to not know which model is it?
But this is a problem you don't just have with quantum gravity. As I said, if there are other particles that have nothing to do with quantum gravity, for example, if you have a grand unified theory of the strong and electroweak interactions at some very high, say 10 to the 15 GeV, which is still very much smaller than the Planck scale, then most likely there would be new particles. And, we have the same kind of problem. Experimentally, we don't have access to those energies. It's a theoretical problem, and it's fine. We can just probe the energies we can with our experiments. It's just how it is.
Okay, so you think it's an engineering problem? Because theoretically, we have some theories which reconcile the two pretty nicely together. We can simply just get out to the energy scale that we would need to test them, or at least test the specific
No,
prediction.
so we have some. So for quantum gravity specifically, because most approaches involve changing the framework, there is those frameworks are not deeply understood. So there is some theoretical work to be done, in my opinion. But again, that's fine. It's not. I don't consider that a big problem.
Okay.
It's just similar to the past where we didn't know how to reconcile. I don't know, the finite speed of light with Newtonian mechanics, and Yeah, there is some solution. We just need to
do some
find.
shenanigans.
Yes.
All right, okay. By having a theory of we call quantum gravity, but let's just give it the name that is most appropriate. Would we ever be able to understand and explain what happened, if not before, at least at the very moment of the Big Bang? Because 1 year ago, when we had our conversation, you we were talking about the lambda CDM model, and you told me the lambda CDM model, which is called the Big Bang model. You said it's not a model for the Big Bang.
Indeed.
It explains the 0.000 seconds afterwards the Big Bang, but we don't know what happened there. Would we be able to explain that precise moment, possibly even before, or could it be forever out of reach?
I can say, I would say a theory of everything would be applicable at the Big Bang, but the Big Bang would not necessarily be one moment. For example, if you have inflation or something like that, you would replace the singularity with something else. But yes, a theory of everything would most likely tell you what happened. It's possible that maybe it will be hard to extract the prediction for the prediction for what happened from the theory, like computationally, like doing the math could be hard, but in principle it would be applicable. A theory of quantum gravity, yes.
Okay.
So I don't think it's out of reach.
All right. Do you think that sometimes, for example, I remember a quote by Stephen Hawking um, saying that if we ever find a theory of everything, then it will simply be sort of a set of rules and equations.
Yes.
Right? And he asks, I think I don't remember in which book, but he says, what is that breathes fire into the equations and makes a universe for them to describe?
What is that brings fire?
What is that breathed fire into the equations? What does sort of get the equations going and makes a universe for them to describe?
Well, I would say the initial conditions. So,
Okay.
so what I said earlier, that's my view at least. The rules for reality, as far as we know, tend to be differential equations of second order. That's our experience with reality so far. So it's a differential equation. To solve a differential equation, you need an initial condition. So you need additional statements that tell you what are the values of the variable of the equations at some point in space-time, for example. And from those points, you start solving the equation. So to me, it's totally part of the problem. The Cauchy problem in mathematics includes both the differential equation and the initial condition. Like just one is not enough.
All right. Well, first of all, I want to mention and congratulate you for the recent appointment for the the achievement of your postdoc
Yes.
in Princeton at the Institute of Advanced Study, which is I believe an astounding achievement.
Thank you.
So I would like to ask you if you could pick any scientist or physicist that you could collaborate on anything that you want. Who would it be and why?
I actually don't know how to answer this question.
Okay.
Many of the scientists I admire and that are very famous and did interesting things do not necessarily work on things I am an expert of. So I don't really know how to answer this question.
Okay.
Like it makes like a similar question that would make more sense to me is like if you're like a kid, what's the scientist that is your idol
Yeah,
or something like that, you know.
Mhm.
But that's a different question. Collaborating with someone means that you're interested in the same problem at the same time, that you have the right expertise.
Mhm.
So there are a whole bunch of other requirements that are completely different, like separate and independent from, oh, I admire this person so much, I
Sure.
want to work with him or her.
Okay. If you could,
yeah.
say, manipulate the conditions such that you have the right level of expertise, everything clicks in, you are working on the same problem, every detail sort of clicks in, and you could pick someone that you can work with on whatever topic that click you together.
I actually don't know. Like if you ask me, okay, I can answer historically.
Okay.
I would say Stephen Hawking, but now he's dead.
Okay,
So-
why Stephen Hawking?
Just because I like the topics of his works a lot.
Okay, which is?
Well, cosmology and black holes and semi-classical gravity.
Okay.
So I like those topics. I like the things he studied.
Okay.
I'm very fascinated by those things, and he's also charismatic. But again, it's not a statement of what I can in practice.
Of course,
do.
of course, absolutely. Okay. What is your research? What will you be doing research on at the institute in Princeton?
Well, I'll find out when I'll be there.
Okay.
For now, I'm finishing my PhD here.
It's a work in progress. Okay, all right. Then I will ask you. You're probably realizing that now you are about to finish your PhD. You're writing your thesis. You're about to enter your postdoc stage, and I can probably guess, maybe I'm wrong, but I can probably guess that you also think of your bachelor or high school or maybe bachelor stage years as yesterday, as very close by, um, or in general, some kind of time distortion. So I want to ask you, what is your relationship with time?
Oh, with time, but like scientifically as a physicist or with my personal life.
You personally, and then afterwards, more scientifically. But first, personally, what is your relationship with time?
I think it's pretty objective. I do not tend to be driven by emotions.
Okay.
So I tend to think about my past life in a very objective way, and I categorize what I experienced.
Okay.
So
Categorize according to what,
like chronologically
Okay,
and,
yeah.
and my experiences. So
Mhm.
yeah, in some sense, I create boxes in my mind where, oh yes, this was the period where I was studying this, and then there was this other period, and so on.
Okay.
So about bachelor and master, I remember those years very, very well, actually,
Okay.
and they were extremely education, like obviously educational years, but like I lived very well in those years. I was very happy in the environment there. So I remember them as a very happy period of my life. And I also went back to the same places where I studied a few times.
Mhm.
So I never, completely forgot the environment.
Of course, of course.
That's it.
Okay. Well, then now, more scientifically
Yeah.
or more, physically grounded, how would you define time? What is time? Maybe you might want to define it according more to first classical mechanics, and then
Yeah.
mechanics, and then general relativity, where the concept of time seems very fuzzy at times.
Yeah, I wouldn't say that in between classical and quantum mechanics there is a huge difference in,
Okay.
in time. It's just the parameter, like a background parameter that describes the evolution of the system. There's this concept of evolution in physics where you have to solve the differential equation. The main parameter is usually the time. You have to find how the things change,
In time.
and the things they change over is time.
Okay.
That's just it. There's just this parameter. That's what time is in classical mechanics and quantum
A
mechanics.
parameter for
Yes,
differential equations.
exactly.
Okay,
Yeah,
all right.
that's
Okay.
really just it. Yeah, general relativity instead does change a bit what time is, because it incorporates it into the space time. So it's time itself doesn't really make sense in general relativity. You have to study it with the other dimensions of space-time. It's not a separate entity. So, yeah, we often hear the phrase time is relative. General relativity makes this very clear. You can change coordinates and describe the same physical system or experiment with a completely different notion of time, and you get the same results.
Okay.
So
Okay.
time in that case is just, well, I have to say, you cannot change coordinates in an arbitrary way. There is one property of all coordinate systems you might choose in general relativity, and that is that among the four directions, in some sense, one of them has a different character than the others. So like different sign, you get 1 minus and 3 pluses.
Okay.
The minus usually refers to the time, but what's the specific direction is not like that changes if you change coordinates. So time is relative, but within some limits.
Okay, all right. When you say you have 1 minus and 3 pluses,
Yeah, I
referring to?
specifically mean the signature of the metric.
Okay.
So the metric is you can think about it as a matrix,
Mm-hmm.
and its eigenvalues will have signs.
Okay.
3 of them have positive sign, 1 of them has negative sign, according to the one of the most used conventions. Roughly speaking, the 3 positive signs correspond to the 3 spatial directions, and the negative one corresponds to time.
Okay. What do the eigenvalues of this metric represent?
They just, yeah, they just characterize they don't represent anything physical, I would say.
Okay. Like
So
what are they? Or let's say what do they describe?
So the magnitude of the eigenvalues don't actually matter, because you can change coordinates and rescale them to have values plus or minus 1.
Okay.
So if the eigenvalue is 2.3, it doesn't matter. You just change coordinates, you make that 1.
So you're only
What
interested in the sign.
matters exactly is the sign.
Okay, all right.
So what I was saying earlier.
Okay. And you were talking about this metric.
Yeah.
So
Yeah, the metric is just an object
Mhm.
that tells you how to measure distances.
Okay.
So if I give you 2 events in space-time, you're interested in the distance in space-time between these 2 objects, you need to use the metric to compute that.
Okay.
And so the distance, so there are 3 directions that have like positive distance, and one of them, some sense, where it's negative. That's the time direction in some sense.
Okay. In which like do you choose the reference frame to measure distances with this metric? So the reference frame, or let's say the coordinates, is it arbitrary or?
You can choose multiple ones.
Okay.
And get the same result nevertheless.
Okay.
So the distance between 2 points in space-time is independent of the coordinate system you use.
Okay. We just talked about this switching time between quantum mechanics, classical mechanics, quantum mechanics, and general relativity. Now, do you think it was pretty crazy for a single man, as Albert Einstein, to come up with all the thing of general relativity?
That is quite crazy.
That is quite crazy,
yes.
compared to quantum mechanics, which was surely the astounding effort of many different men throughout a longer span of time, whereas Albert Einstein, let's say, only 10 years only, but came up with a revolutionary theory.
Yes, I find that incredible.
Okay.
I mean, Einstein did not invent all the concepts he used, for example, differential geometry. But the fact that he used all those concepts that previously were never used in physics. And he came up with the idea of using them and constructed such an incredibly beautiful theory and also accurate experimentally alone. That is, yeah, in my opinion, one of the greatest achievements in the history of physics.
Yeah, it's pretty
It
insane.
really takes a genius sometimes.
I have been watching the video of three scientists. I think one psychologist, a neuroscientist, biologist. I don't remember the third one. They have analyzed the brain of Albert Einstein, and
Yes.
they because if anyone does not know, they after Albert Einstein died, they went to his family and they asked him, "We will never have a chance like this to study the brain of such an incredible genius. Can we study his brain?" And they found, I think, a sort of overdeveloped area of the brain, which they said could have been correlated. I don't remember precisely with sort of a higher or more prolific, more intense brain activity.
Actually, the story I knew is
Mhm.
slightly different. Is that
Okay.
the doctor that was I don't know, dealing with his corpse after his
Okay.
death secretly
Oh, did it? Oh,
took the brain without permission.
okay.
That's the story I know. I don't. I'm not sure whether
I heard it
which version
from
is right.
I heard it. Okay, that's probably my story is false, and it's the I'll say the formal one because I heard it from the World Science Festival, and there was Brian Greene and
I see.
many other scientists. So probably that's what they say in the in the public. Probably.
I see. We should check.
Okay, all right. Um, is time, as we are talking about before, is time a fundamental or an emergent property of our reality?
Yeah, that's a good question. Probably my answer would change based on the context. So, for example, uh, time in a cosmological sense, I would say that um, the concept of time relates to the flow of entropy cosmologically. So entropy increases,
Mhm.
and that defines the arrow of time. So in some sense, it's emergent. Um, and that is linked to the cosmological evolution.
Okay.
If you think about frameworks like general relativity, then the time there is a fundamental concept in the sense that it's part of the one of the tools you need to define the theory, so a coordinate system.
Mhm.
But those two times are not necessarily the same. Those two concepts of time live in different contexts, in my opinion.
Okay. Is for example, sometimes when I think about emergent phenomena, one thing which is discussed or debated is the fact that, for example, atoms or particles, if I'm right, they do not have temperature. Right, like a single atom does not have
Sure.
temperature, but a bunch of atoms, let's say,
I guess you can still define temperature of one atom. But okay, I get what you mean.
sorry, what do you say?
Can in principle define the temperature of like one atom, I think.
Okay,
But okay, I get what you mean. Yeah.
okay, and a, a group of atoms can be formed to have a temperature. So temperature is
An emergent property,
an emergent
yes.
property. Okay, do you find, let's say, not strict mathematical analogies, but do you find analogies in the uh, how to conceptualize the emergence of time?
Yes, only one of the examples I was making before.
Okay,
Not in all cases.
okay.
So,
In which,
for example, the cosmological
yeah,
example I was making
okay,
before. In that case, it's totally an emergent property.
okay,
But that depends on the initial conditions of the universe.
okay.
Once again, we read And no, yeah, that's it. Other like time in different contexts does not to me look like an emergent.
Okay. What is the difference between is the difference between space and time in general relativity simply a matter of which coordinates? Sorry, that space is a simply different triplet of coordinate and time is a.
No, they are part of the same entity.
Mhm.
You can choose a different coordinate system, so you can describe the same manifold, so the universe, in different ways, as long as there's one time direction and three spatial directions, but you can change how these directions are placed on the manifold. And yeah, that's it. They are part of the same entity, so they're not treated differently. Time doesn't have a special treatment in general relativity. It's not different from spatial coordinates. It enters the computations exactly the same way. The differential equations that we need to solve involve space and time mixed together.
Okay. Is it, or let's say, how big of a step is to go from the classical space and the time to the space-time of general relativity?
I think it's quite a big step. And indeed, it took a genius leap from Einstein to the jump. It's because, it's not very intuitive. Every day we experience time as very different from the spatial directions. So it's not like the notion of space and time in general relativity is something that you cannot very easily guess if you don't know that.
I bet.
So yeah, it's quite a bigger change of perspective. Yes.
And what does it mean? I've heard this explanation multiple times, and I kind of got lost in the math explanation. So I would like to see if I can understand it, if I can hear it one more time. What does it mean that space and time swap inside the horizon of a black hole?
Yes. So it means that, as I heard before, there is one direction that corresponds to a minus sign, and three directions that correspond to plus sign. Okay. Now, outside the event horizon, the radial direction, so moving radially, so towards the black hole or away from the black hole, corresponds to a plus sign.
Okay.
So that corresponds to a spatial direction. Inside the event horizon, that corresponds to a minus sign.
Okay, but how?
It's if you look at the metric of a black hole,
Okay.
You can see very easily that the sign changes.
Okay.
And both signs change together. So the radial direction switches from plus to minus when you cross the event horizon.
Okay.
And the time direction switches from minus to plus. So in practice, what this means is that while outside the black hole, you can go you can only go forward in time. Inside the black hole, you can only go inward radially.
Okay.
So,
but then if the time direction has changed into space direction,
yes,
does it mean that you can go back and forth in time, which is the new space?
well, in some sense, yes.
Okay.
But time has an end. Time ends inside the black hole, inside a non-rotating black hole. The singularity at the center is actually a so-called space-like.
What does it mean?
part of the space-time, it means that it's a single moment in time rather than space. So that's called space-like. So it means like inside the event horizon, you can only move radially in the same sense as you can only move forward in time outside, and the time, yes, behaves like space. So in space you can you can have a limit for if you live on a circle, space is finite because it's bounded by the length of the circle, and inside a black hole time is finite, just like space is finite
Okay.
outside it, like
Okay. Now, when you're telling me this stuff, I am trying, like my brain is trying to go, like completely leave all common intuition and try to venture into this very weird functioning. Now, do you believe that this, I hope you agree with me, weird functioning, weird process of, at least weird to our common intuition, will it become somewhat common knowledge, in sense, will it become intuitive that non-scientific or non-experts will be able to understand it without much friction, or will it be, not forever, but will it be for still a long time to go, something which is sort of has a deterrent from being understood
so
intuitively?
the latter. I think
Okay.
it will be always hard to understand
Okay.
critically. I do think that popular science explanations get better over time,
Okay.
because over time, even long time, like decades, we figure out better ways to explain the same concepts. Maybe because we understand the concepts better and better. And it's true both with popular science and how we teach
Okay.
science and physics in particular. That being said, I think concepts like black holes and how do they work will never be like available to someone who doesn't study physics, just because we don't experience those in everyday life. So we don't build intuitions for those things. We just need to write down and do computations and look at them. That's the real way to understand them.
Okay. Okay. What is the best picture to have in mind when thinking about general relativity and the curvature of spacetime? Because in popular science videos and explanations, what is usually the case that they place a rubber sheet, they place a big ball in top of it, and they throw marble around this big ball, the marble spiral inward, and they say, look, this is the curvature of space-time. But in the problem, at least from what I saw a couple of days ago from a tweet of a physicist, is that this analogy gives the impression that the curvature that makes, in this case, the marble or the moon spiral around Earth is the curvature of space. But he said that what is actually making a planet or the marble spiral around an object is the curvature of time, because the curvature of space is not as significant as the curvature of time. Or is
Okay,
the
that's a bit
analogy?
surprising. I think you need both. I think
Okay.
both time and space are curved. Like around the sun, there's a change in like both time and space actually are curved by a very similar factor.
Okay.
So yeah, are curved in a similar way, as
Okay.
far as I know. So
So is the rubber sheet analogy
I
somewhat
think
accurate?
it's a toy model that you can show to kids.
Okay. And what is your picture that you as a...
I might disappoint you. My picture is just mathematical.
Okay, all right.
Like seriously.
And what do you think about, like, what is
You
the
do not
mathematical touch?
you do not need to visualize things.
Okay.
You can get intuitions about these things by writing down equations.
Okay.
I know that sounds very dry, but how do you really understand the concept? But yeah, the answer is with the equations. If you get familiar with those, you understand how it really works.
Okay.
So I cannot visualize the fourth dimension in my
Right,
mind,
probably, yeah.
let alone curving a four-dimensional space-time, right?
Yeah.
Because even with the third dimension, I can visualize three dimensions, but visualizing three curved dimensions, it's much harder because usually we imagine that as embedded in a larger space. You know, if you have a two-dimensional curved surface, you need to, like, to visualize it, you need to embed it in a larger space, like a sphere, like the surface of a sphere is two-dimensional, but it's embedded in three-dimensional space.
Okay.
So even with curved three-dimensional space, I would need to picture in my mind the fourth dimension
Embedding, yeah.
to visualize it.
Yeah.
With four-dimension curved space, it's even harder. So I don't even try to visualize it, but I don't need to visualize it.
Okay.
I don't need that to understand how it works.
Okay. All right. No, I like this explanation. Well, I want to talk about what you said before, the black hole singularity, because you said it's a point where time ends.
Yes.
Does it represent sometimes the sort of a debate? I mean, there is of course much debate, I would say, behind it, and they say, might it be only a mathematical construct to say, okay, there we have no idea of what's going on.
Yeah,
We call
I
it
think
singular.
everybody would agree with this.
Oh, okay, all right.
It's just that the theories we currently have point out to that point in space-time as somewhere where our theories don't apply anymore and something probably interesting is going on, or we don't know what's going on.
Do you think okay, well, probably this question is related to whether we will find out about quantum gravity, but do you think that we will explain what is happening at that point, at that precise point?
So quantum gravity would be able to tell you what's going on there.
Yeah,
Yes. Whether we
can test it.
well, no, we cannot test it because then we cannot communicate with the outside of the
Yeah.
black hole. Whether we will ever be able to use a theory of quantum gravity to compute what happens there, I don't know. It might be exceedingly hard to do.
What do
I
you
have no
mean?
idea.
What do you mean when you say whether, like what you just said, whether we will be able to compute what the theory tells us?
Yeah.
Uh,
Sometimes we have a theory, but we don't know how to extract predictions out of it.
okay.
So think about quantum chromodynamics, the theory of quarks and gluons. So that theory, in principle, protons and neutrons are predicted by that theory. But it's so complicated that from the equations we cannot just sit down and write down some computations and find out the mass of the proton and the mass of the neutron. This can be done in some sense computationally. Some people have figured out a way to do it in an approximate way with the computers.
Okay.
But extracting predictions from theories sometimes is extremely hard.
Okay.
So you have like even the degrees of freedom appearing in the equations of quantum chromodynamics, quarks and gluons are not the ones you want to talk about. You want to talk about protons, neutrons, and pions. So these are emergent concepts from the fundamental ones.
Okay.
So you need to understand how they come about.
Okay. The universe is weird.
Yes.
It's very strange in its functioning. What is the weirdest thing about quantum mechanics?
The weirdest thing about quantum mechanics.
The thing because I have an analogy to give you. I studied the complex analysis during the first semester of this year. And in complex analysis, we have very weird results, very counterintuitive compared to what you saw in real analysis.
For example?
Well, for example, the Casorati-Weierstrass theorem. It's a theorem about essential singularities, and it says that
you get all the values but one.
Yeah, you basically get the whole complex plane just by evaluating your function around that singularity, which is most of the times, and also like pi apparently, of course not precisely, but apparently is a multiple of every integral. But yeah, appears in
Yes.
the integral. Now, what is something that you say, okay, this cannot be the case for quantum mechanics, yet mathematically?
So I'll say entanglement.
Okay.
But more because this is what makes it more different from classical mechanics.
Okay.
And so it's maybe the thing that is harder to understand over quantum mechanics to me. So entanglement is the fact that you cannot describe. So if you have two entangled particles, it means that you cannot describe one of these particles independently from the other one.
Okay.
Any complete description of particle A must involve some description of particle B as well. And this is a very weird concept. Intuitively, it doesn't make sense to us because we live in a classical world. To me, entanglement represents the biggest change of paradigm that quantum mechanics brings about. So I would say it's that to me.
Okay. And what is the most beautiful, maybe not precisely weird, something that you say, oh, this is very elegant in probably both the mathematics, I mean, probably
quantum mechanics?
Yes, in quantum mechanics.
Elegant. Well, I don't know. The equations are very elegant, are very simple. Schrödinger's equation is very beautiful.
Okay.
It has a lot of properties in it, like the unitarity of time evolution.
What is it?
It's basically the conservation of probabilities.
Okay.
So you don't lose, you don't leak out particles or probabilities from the system, from a box, from a closed system. That's unitary, roughly.
Okay.
What
does it tell you that because the Schrödinger equation, correct me if I'm wrong, simply predicts, given the initial conditions, right, predicts the evolution, the time evolution of a system.
Of the wave function, yes.
Of the wave function, okay. But predicts only probabilities. So what does it, like it predicts the probabilities that this system is in a certain state?
No, not quite. You need something else to go from the wave function to the probability. So Schrödinger equation just tells you how the wave function evolves.
Okay.
And then you need some prescription to link that to the measurements.
Okay. Which is
Bob's rule.
Okay. But what does it tell you that the fact that quantum mechanics, which is one of the most effective theory in explaining reality, predicts only probabilities? Like, how can it be that nature seems to be
funny.
probabilistic at its most fundamental level?
That's one interpretation of quantum mechanics.
Okay.
It's quite funny. I tend to think that the weird phenomena that happen when talking about measurements in quantum mechanics have to do with an illusion that we have because we are classical systems, and these illusions come about when we interact with a quantum system, and we interpret its measurements of it classically.
Okay.
So yeah, I tend to think you can describe classical systems like the 10 to the 25 particles I am made of.
Okay.
With quantum mechanics, but when numbers are so large, all these collective description of particles, we have some emergent property that creates the classical word. But that's still describable with Schrödinger's equation. And so the act of measurement, I see that as just, so Bond's rule, I see that as an effective description of these extremely complicated interactions between a quantum system, so with a small number of particles, with a classical system.
Okay. So, is it ever in principle possible for a classical systems like us to probe the true nature of reality, or are we forever bounded before probing into a certain layer of understanding of reality? Because this reminds me of, not reminds me, but one thing I can think of is the meaning of the uncertainty principle. Sort of puts a lower bound to the accuracy of a measurement.
I don't like to think about it this way.
Okay.
I like to think about the uncertainty principle as not a bound of what we can measure, but a bound on the properties particles have. So when we say that we cannot measure position and momentum of a particle simultaneously with arbitrary precision, what it really means to me is that the particle itself doesn't have well-defined position and momentum at the same time.
So it's independent of the measurement, you're saying? Like
Yeah.
it's.
I would say it's just, so the mathematical structure of quantum mechanics does not allow for those two quantities to be well defined at the same time.
Okay. Okay, what does this tell you about the fabric of reality? How can nature, on the very fundamental level, be not as precise and definite as we classical systems like to think of it?
I think it can still be precise. It's just that concepts like position and momentum are classical concepts.
Okay.
Are properties that we like to think about and we can measure classically. So I want to define them for a quantum system, but the language of quantum mechanics involves different objects, wave functions, operators, and so on. So when we try to link the quantum mechanical objects with classical objects, we find that the classical description is not very powerful or accurate. And so you run into these difficulties like the uncertainty principle. You might want to, have a completely classical description. So you would like to measure both position and momentum, but you find that you can't. Because the quantum mechanics doesn't allow you to use that description.
Okay.
It's not appropriate.
So basically, like what you're saying is not humans are restricted from probing nature with such an accuracy. Is simply nature that does not is not constructed with the accuracy that we think of giving it classically.
I don't think the uncertainty principle is a statement about the accuracy of nature. Or I don't think about the uncertainty principle this way.
No, but in general, like sort of the implications it might have on the fabric of reality. The fact that there is no precision, there is no straight edge precision in both momentum and position at the same time for a particle.
But why is that a problem? You can take a one-dimensional quantum system with one particle that can go back and forth along that line. And you have an absolutely accurate and precise description of what's going on through Schrödinger's equation. And the wave function of the particle tells you everything you can possibly know on all the questions you can possibly ask. Are like the answers to those questions are in the wave function of the particle. You can compute how that evolves over time. Position, and you can ask what's the position, what's the momentum, and the mathematical structure just doesn't allow you to have precise answers to both questions, because the quantity you're asking for is not one of the fundamental tools the system, the mathematics of the system uses.
Okay. Okay.
But the description is accurate and precise.
Okay. You mentioned the wave function. Is that a real object? It's just a mathematical shenanigans that works very well, but we don't.
So to me, talking about real objects doesn't mean much sense per se.
Okay.
So I like to call something real if it's a good description of reality.
Okay.
So I would say yes, it's real in the sense that it works. Okay. Whether it exists or not, I don't know how to even define that. It's a good mathematical description of the reality, then I would say it's real. Okay. That's it. I don't need to know anything else.
Okay. Do you think do we have some limitation in sorry, are there some limitation in our understanding of the collapse of the wave function, in the sense that there is probably much more in the collapse of the wave function than we currently know?
So this is related to what I was saying earlier about the measurement in quantum mechanics. So we have, Schrödinger equation that tells you that the time evolution is unitary. So it has this property of unitarity. And then the rule that you use to link the Schrödinger equation to the measurements is non-unitary. So this is Born's rule. And it tells you that the wave function, well, it tells you different things. One of them is that the wave function collapses. Now, this is a non-unitary process. I interpret, so my interpretation of these rules is that they are an effective description of what actually happens. I believe is a weird word to use. I like to think, I expect that the measurement process is still unitary. So it's still described by the Schrödinger equation. But because it involves a large number of particles, when we do a classical measurement, when we classical beings interact with a quantum system, describing what happens is so hard that we found this effective description, it's the collapse of the wave function. So if you look at the quantum system only, it looks like its wave function is projected onto the eigenstate that you corresponding to the eigenvalue you measured. And yeah, that's how I interpret the collapse of the wave function.
Okay.
So I'm here. The focus is on the unitarity of the time evolution of the universe. So involving the quantum system and the measurement apparatus and so on.
Okay. Jim, you just mentioned, you just said believer is a weird, is a strange verb to use for you, which I see, I can really see why. Can I ask you, what is your definition, if you have one, for God?
I don't really care.
Okay.
I don't know. I don't care.
Okay.
In a very precise sense, actually. I don't care about anything outside my past light cone. Not really.
Okay.
So I observe that the reality I can interact with is well predicted by the laws of physics, and I don't need anything else.
Okay. So you believe there is nothing else other than maths? believe.
That I believe.
You think there is nothing else?
Like, if I want to describe the physical reality, if we want to do that, using mathematics is by far the most successful way to do it we have found so far. And I don't need anything else.
Okay, so there is nothing else other than math that permeates reality. That is your reality.
Yeah, I would say so, yes.
Okay. Are you scared of death?
Yes, in the sense that I would like to live forever to witness the future scientific discovery.
Okay. Okay.
I'm afraid of dying too early and not be able to witness what we will discover in 50 years.
Okay.
But that's just it.
And what is your like? Do you think it is just very scientifically? It is just on-off switch after a person die?
No, of course not.
What do you think? What is that? You think in regards?
No, it's just biological thing. So you can be brain dead, but not like some other bodily functions may still work. No, it's just there's no sharp boundary between life and death. I think it's pretty clear.
Okay.
Especially for very complex organisms like a human. There are so many things in our body. It's absurd to think that in the same moment they all switch off at the same time. It's just biological processes.
And there is nothing else after the brain death. So after your brain shuts down, let's say overall, that's the end. That's it.
The end for what? That's not the end. The world continues.
Okay, wait.
Forward.
Okay, wait a second. The world outside you, but you are sort of your world. Like when you wake up, a world, a reality projects to you. You see only one reality. This reality is not there anymore because you don't have the capacity to project that reality anymore.
Yeah, so it's like when a computer breaks.
Okay.
So the things going on in my brain stop working properly. And so in that sense, I die. So the world stops for me. So my brain is no longer registering
Information.
what I see, what I smell, and so on. Just like if you have a computer with a microphone, like in this case, maybe the computer breaks at some point and it stops receiving inputs from the microphone. That's the same thing.
Okay. How do you come to terms with the fact that many or some or just a few of the most interesting questions that maybe you are working on or maybe questions that you are interested in might never in your lifetime come to an answer?
Yeah, it's unfortunately one of the curses of human nature. We have
Our own
finite lifespan, and actually even worse, scientific discoveries nowadays take longer and longer than in the past. Like in the 20th century, so many discoveries were happening one after the other. Now experiments take so long because they are so complicated and advanced. So I really hope I will witness future discoveries, but I cannot be sure. And yeah,
Would you accept to, or would you try? Would you want to biologically enhance your lifespan to witness these
of course.
scientific discoveries? But then, wouldn't, okay, for how long? Let's say until
as long as I can.
Okay, but then don't you think it's a little bit not contradicting, but sort of defying what you just said before, the human nature. The one of the main properties of human nature is the finiteness of our time, of our life. If we can um, just increase, if we can increase the span of our life, aren't we sort of defying this property, which is intrinsic in the human life since the beginning of life?
Yes. I mean, I'd like to change that. Why not?
Okay. All right.
I don't. I mean, it's probably not going to happen.
Sure.
But I don't think it's there's any fundamental um, like there's any law of physics that prevents you from doing that. It's just not how life on Earth works.
Okay. Okay. Then can I ask you, would you biologically enhance or let's say foster an adoption of biological engineering of human beings to achieve higher and more powerful brain capabilities to develop and progress humankind with all the
You
risk
mean,
that
well, the
comes.
question is whether I would do like genetic engineering on humans?
Yes.
Yes, totally.
Okay. What would you? How would it?
Like if we
What would you do?
discover how to make a newborn more intelligent, yeah, I would
Okay.
pursue that totally.
Okay. And what would be your not end goal, but what would you be your short-term objective in doing this process?
I mean, first of all, it sounds interesting, so why not?
Okay. Okay.
Um, but second, I care a lot about scientific discoveries. And it seems like there's a pretty clear link between brain power and capacity of doing scientific discoveries. So
Okay.
if we can increase brain power, why not?
Okay. Do you believe? Do you think that the ethics involved in doing such a thing might be unbearable, or let's say might be so restrictive that such a thing could never actually be achievable?
But ethics is something that doesn't exist
Okay.
before humans.
Okay.
So ethics is what we as a society decide, like a way we decide we should behave to create a better world for everybody to live in, so you can live longer, happier, and healthier, and so on. That's what ethics is. There's no one that tells you, oh, that's how you should live. It's just that we agree with each other of a way to live. So yes, doing genetic engineering on humans would cause some people to think this can bring harm to our society, and so those people would consider this unethical. But if this will ever become possible, I would hope that this perspective might actually in the end lose to perspectives that promote these practices.
Okay. Is it intuitive for you, or have you built an intuition now, or you are just lost and don't even hope anymore to make sense of the gargantuan numbers that we have in cosmology? Because sometimes when I um, listen to videos or hear people speaking about cosmology, they mention yeah, I don't know, well, 10 billions of light years in distance, stuff like
Yes.
this. And I hear, okay, but he just put a number, he just gave a number like this, very simply. But do you actually like realize how large is that number compared to our scale, or after some time studying and working in this field, you simply put aside your need for intuition and you just stick, as you said, to the maths and to the equations.
But like my intuition is math.
Okay.
I wouldn't say that with mathematics I don't get intuition.
Okay.
So, for example, with very large numbers,
Mhm.
mathematics gives you the tool of powers, so powers of 10.
Mhm.
And so if you understand what a power of 10 is, then that's all you need.
Okay.
If what's a light here, 10 to the 16 meters,
Mhm.
something like that, and 15 maybe, that's a very large number, but that notation with
Okay.
base and exponent,
Yeah.
if you really understand that notation, that's all you need to know. That's it becomes intuitive.
Okay. And how have you built how is it or let's say what is the intuition process that goes behind in your mind when you are talking about millions, billions of light years, or for black holes uh, like 30, 40 billion times the size, the mass of the sun in some cases. How did you build intuition for that? Simply just by practice, or is there, I don't know, a specific process that helped?
I guess by studying mathematics, I just understand what numbers mean,
Mhm.
and that's about it.
Okay.
But is this something that this, at least I got this kind of intuition, if you want to call it intuition, at a very young age, so
Mhm.
studying at school.
Okay. All right.
I don't think it's a problem for scientists that
Sure.
dealing with these numbers.
Of course. Um, do you find it ironic or reasonable or just as it should be that, as far as we know, um, our consciousness and awareness and understanding of our surrounding is found only at our scale, which is not precisely, but very roughly, in between the microscopic scale of quantum mechanics and the huge scales of cosmology.
That is quite funny. That's quite funny. So first of all, it's not clear a priori why there should exist such different scales in our universe.
Mhm.
So the size of the universe very roughly depends on the size of the cosmological constant in some sense. Like the naive expectation for the cosmological constant would be a much larger value than it actually is. So if that was the case, the universe would be much smaller. It would have the size of a microscopic object.
Okay.
Instead, the cosmological constant happens to be extremely small, and so the universe is very large.
Mhm.
That's yeah, we don't know why is that. We have some ideas, but it's a very hard problem. And instead, the size of the microscopic world depends on another fundamental constant of nature, which is the electroweak scale. So the typical energies of the particles of the standard model, roughly speaking. And why these numbers are so different, yeah, it's a big mystery. Why we lie in between those numbers, that's funny. I wouldn't say that's a mystery. It's just funny. It's funny that at that scale, so interesting emergent processes happen. At such an intermediate scale.
It's singular. It's a very singular case.
It's very strange. Yes.
Do you think there is you just mentioned about this constant of nature? We can probably go on for hours talking about how well the constant of natures have are fine-tuned for life. Do you yourself personally need an explanation for this fine-tuning, or you simply accept the randomness in it and you say dynamics plus initial condition, and that's just it.
So that's an interesting question. Many times anthropic arguments are used to explain,
Okay.
say, the constants of nature.
Mm-hmm.
And so the argument is usually we could not see, say, fundamental constants with different values because otherwise life would not form.
Yeah.
So we wouldn't be there to measure those values. So
Okay.
these are the only possible ones we can measure.
Are you
I
satisfied
think
with such a?
not really. I think it's possible that ultimately an argument of this kind might be needed in some cases.
Okay.
But I think like from experience from the history of physics, many times we did in fact find explanations for for what we were measuring and like finding in physics. So I think it makes total sense to try to explain why the fundamental constants have the value they have without assuming anthropic arguments.
Okay.
Because chances are there is a deeper explanation. Then maybe, yeah, at some point, maybe we need some anthropic arguments, but I wouldn't say that is a good reason to stop searching for other explanations.
Okay. So does it even slightly satisfy you an anthropic reasoning? Because to me, and I am of course less well aware of the big picture, but it doesn't really satisfy me at all because it very brutally say, okay, it is what it is. So there is life because if it didn't, if it weren't um, like it has been, then we wouldn't be observing it.
So to me, anthropic arguments are more satisfactory if they include a compelling reason why other possibilities might also exist.
Okay.
So there's a famous argument by Weinberg from 1987, I think, about why the cosmological constant is so small. And the argument, I mean, actually, the cosmological constant wasn't even measured at the time.
Okay.
And so he wrote this paper writing the cosmological constant couldn't be larger than this value, otherwise galaxies wouldn't form,
Yeah.
and so on. So life wouldn't form. And then a decade later, the cosmological constant was measured. It was roughly the same value as Weinberg predicted in some sense, right?
And what is the reasoning you made?
So the reasoning by Weinberg is that so it doesn't just involve anthropic arguments, but it involves a plausible structure in string theory where you have a very, very large number of vacua. So, say, possible universes with slightly different values of the fundamental constants, including the cosmological constant. And there are, like, it's a plausible scenario. It's not made up. It makes sense in that framework, in string theory in this case. And all these universes has slightly different value of the cosmological constant, for example. And Weinberg argument is that only in a very small number of all these universes, which maybe they all exist, only in a very small number galaxies form. And structural formation goes on, and then you can have life. So this is a bit more satisfactory because it fits in a context where a larger number of possibilities have equal right of existing.
Okay.
But they do not lead to a universe like we see.
Okay. Do you think this argument, or well, probably better, the inflationary theory of cosmology, do you think there is a compelling argument in favor of a multiverse, which is being abused as a term, but in sort of the meaningful way of the multiverse?
I think it's a reasonable scenario in some cases,
Okay.
some proposals. Yeah,
Okay.
could be. It doesn't really matter though.
Why? Because they are disconnected from our universe.
Yeah.
Okay. Okay. Well, if there is this inflationary stream, which leads to the description of cosmology as eternal inflation, something that is eternal is a synonym is just infinite. What is to you the concept? What does infinity mean to your finite mind?
Once again, mathematics.
But how do you do it? Like, how do you? Okay, mathematics. I understand, but mathematically, how do you try to intuitively grasp the concept of infinity?
There are several kinds of infinity in mathematics.
Yeah.
With different properties.
Yeah.
And I build the intuition on those properties. So there
Okay.
is Aleph naught.
Yeah.
The
size of the natural number.
Exactly, the smallest infinity in some sense, and then there are others, including the continuum, which is a higher ranked infinity, let's say. Why do you need intuition? But like, is it that hard to picture intuitively the infinity of the natural numbers? It's not that hard. Like 1, 2, 3, and dot dot dots. That's it. What else do you need? What else are you looking for?
Okay, then how do you picture the continuum? The size of the
The
unit
continuum,
interval?
I picture it as not just dot 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 far away from me, but also if I take a magnifying lens, I can enlarge it and enlarge it and enlarge it, and it's dense in the same way at all the magnifications.
So is mathematical space infinitely divisible?
What do you
So
mean
a
by
real
that?
line, like if you picture the real line, or let's say if you have the mathematical real line in your that you're working on, you can infinitely magnify this line and always find another real number just by magnifying the
Sure,
expression.
any interval of the real line
Yeah.
contains a continuum, contains as many real numbers as the
Yeah.
the real line. Yes.
Okay. Then why do you think mathematical space is infinitely divisible, but physical space is not?
So, first of all, I wouldn't say mathematical space is infinitely
Sorry,
divisible.
mathematical space,
It's just
mathematical line.
this is a property of the real line.
Yes. Okay.
Physical space, well, I never said that I think it's not infinitely divisible.
Okay. Okay.
Though there are reasons to believe there is a kind of fundamental constant with the dimensions of the length, which is the Planck length, and some results from string theory seem to suggest that probing distances smaller than the Planck length is in fact kind of the same as probing distances larger. So in this case, it could be that it's just mathematically equivalent. So it doesn't make sense to divide the space in physical space in smaller pieces.
Okay.
Because you will be finding things you had already at larger scales.
Okay.
But like, I do not think about physical space as divided in cells of a fundamental length.
So basically, you don't agree with loop quantum gravity.
To be honest, I don't really know how that works.
Okay. They simply say, I only know this thing. They posit the existence of a quanta of space-time, which is basically the most fundamental building block according to their theory.
Could be. You don't have this in the more mainstream proposals. To be honest, I remember when studying quantum mechanics, some people, especially some mathematicians, were like kind of expecting to like quantization to mean something like defining a fundamental unit of quantities, including space or maybe even time. But you don't have such a thing in quantum mechanics. Quantization doesn't mean that. It just means using a certain mathematical structure, which then, as a consequence, implies that some quantities like the energy come in discrete packets, but there's no prescription a priori about space and time.
Okay. Instead, what about an infinite space? So an infinite universe? Again, if I ask what does it look like in your mind, then you will say it's just the maths. But how do you, how do you try to understand mathematically, if you do, an infinite universe in space and in time?
But that's not really relevant because
Okay.
our observable universe is finite anyway.
Okay. Okay. But
So
there
yeah,
could be.
you can imagine that the universe goes on and on forever. Sure, could be.
But you just don't
I
care.
have to say I don't like that idea very much.
Why?
I don't know. I like the idea of a closed universe a bit more
Why?
because I guess it's related to the fact that if you have an infinite universe, then you also have an infinite number of possibilities. So eventually, you'll find whatever you can. So like finding explanations feels a bit less meaningful
Okay.
in an infinite universe because you can always say, yeah, whatever. It's just anything can happen. So this just happened.
Okay.
It feels a bit less meaningful, like an infinite universe. While if you have a closed, like a finite universe, to me it feels like the wonders it contains have more meaning. They are more surprising
Okay.
because they are a finite number.
Okay.
But it doesn't really matter.
Sure. And you said that it is less meaningless. So you say that something has or we assign meaning to something based on the fact that it can potentially be unique or at least not infinitely replicable.
Well, in some sense, I guess so. Yeah.
Okay. Um, if we ever try to find a trace of multiverse cosmology, of a multiverse through inflationary theory or through anything else, how do you think we could find a trace of these other universes? Which, to be honest, when I mean universes, I simply mean probably other patches of universe, like not the. Sometimes a very common image is given as these bubbles floating around in some space, simply as a neighborhood patch, okay, that we know that we cannot see.
Yeah, first of all, I'm not an expert, but I don't see how we can experimentally get access to these things.
Maybe to the
Most
extent that.
likely, what we can do is to learn more about inflation. So we can do observations in cosmology and astrophysics and learn, about a precise model of inflation, and then maybe from there we can compute the likelihood of this kind of scenario.
Okay.
And so maybe we might conclude, okay, if this is indeed the right model of inflation, then it also predicts the creation of other bubbles and so on.
Okay. All right. What to you is the meaning of the universe? If no meaning at all.
No meaning.
Okay. Okay.
What do you mean with meaning? What kind of
Like
answer
what
do
you
you
said.
expect?
No. What the answer? Well, I don't. I mean, anything. Like I expect literally any answer. Nothing can be no meaning can be one of these answers, according to the definition of meaning that you gave before. So you gave meaning to something, whether it is
Yeah, no, but that was more my personal satisfaction.
okay,
That's what I meant.
okay,
Personal satisfaction in finding an explanation for the things I observe. For the universe, I find it extremely interesting and fascinating. Well, that's just my opinion. About the meaning of the universe, I don't know. Meaning feels a lot like a human concept, and my views about physics and the universe are extremely non-anthropocentric.
Okay, okay. Can you tell me if you agree with this um, sentence or this description, or what do you think about it? I read the book of Lawrence Krauss, I think, a cosmologist, a researcher, and he said when delving into the question, the very famous metaphysical question, basically, why is there something instead of nothing? He says this question does not have to be answered because the why might not want to reveal itself because it's a different type of why compared to the whys we ask within the universe. They are embedded, these whys are embedded in the universe. Answering them, we take advantage of the features of the universe we know, but the universe itself, as far as we know, is not embedded in anything. It can just be.
I agree. It feels like a different why than the ones we usually ask in science. That's what I have to say.
Okay.
That's
So it is a why that defies the sort of causal.
It's a philosophical why, not a
Okay.
scientific why.
Okay. All right. What is your relationship with ChatGPT?
ChatGPT, so AI in general.
Yeah.
In my office, I'm almost the only one that does not actively use AI in research. I find it very interesting. I mean, I'm a bit of an outsider, but I do follow advancements in AI. It's quite interesting, quite useful. Well, not maybe in its current form, but maybe in the future. Yeah.
Okay. Do you think artificial intelligence, surely not in the form that we have now, but in a developed way, do you think artificial intelligence could win a Nobel Prize in the 21st century?
So I suppose with these you mean whether it will become intelligent enough to compete with the best physicists.
I mean, yeah.
I don't think anybody will award a Nobel Prize to ChatGPT.
No, not to ChatGPT.
We will not like an artificial intelligence.
Yes, okay.
Nobody will ever do that.
Okay. Even if the discovery made is of the relevance possible.
Yeah, then the Nobel Prize will go to the person who devised that artificial intelligence tool, right? That's what people will reasonably do in the future.
Okay.
Doesn't make sense to give the Nobel Prize to an AI. That being said, the real question is how useful, how powerful will artificial intelligence be in the future? I don't know. I think it will be. I have the impression it will be quite important, but let's see.
Okay.
Let's see how it evolves.
Okay. I want to ask you, sometimes there is, sorry, what I said before about biological engineering, the biological genetic modification, sometimes is the case that people say, what if ChatGPT had consciousness, or what if artificial intelligence has consciousness, or this kind of stuff. Sometimes when I talk about the biological engineering of human beings, what I sort of mean is sort of the reverse process of what I just said, meaning you put into humans, which have consciousness, which we will define in a moment, not now, you put into humans the processing power of an artificial intelligence. So you have a higher retention power, you have higher memory, higher learning, whatever, and it's into a system, a human being, which has the capacity of reasoning and of conscious and aware reasoning. What do you think of this idea?
You mean whether I would pursue this if it was practically feasible?
Yes.
Yes, the answer is yes.
Okay.
Of course, I would be would like to be more intelligent, have more computational power in my brain.
Sure. Do you think that the other way around, is it ever achievable? So because maybe
Give a body to ChatGPT.
yes, give a sort of okay. Let's say that a sort of consciousness, sort of a self-awareness arising in artificial intelligence, and yeah, these type of devices.
Might be.
Okay, does it? You seem pretty, I would say, chill about it.
Yeah.
Doesn't it scare you? The fact that things which are not strictly life form can develop a sense of consciousness.
But both life and consciousness are not necessarily sharp concepts.
Sorry, you said are not necessary?
Sharp.
Okay,
Sharply defined concepts.
true. That's very true.
So I don't know. I mean,
Why
maybe
not?
maybe we start saying it's alive if it shows consciousness. What's wrong with that? Then we create a new um, live being.
Okay.
That's cool.
Some bionic
Yeah, why
robots.
not?
Okay. If you had to explain to ChatGPT what does it mean to be conscious? How does it feel to be conscious? What is the experience of consciousness? The experience of being between your eyes to an
Yeah,
artificial
I'm
intelligence?
afraid I don't really have a good answer for this because it's a bit hard to define. I think it's all about self-awareness.
Mhm. Okay.
So it's about the ability to put yourself in relationship with the environment and with yourself.
Okay.
I'm afraid I'm not really able to dive more deeply into
Mhm.
this definition. It's quite hard to do.
Yeah. What is the difference between or let's say, what is the difference then from consciousness to awareness?
Mm, I don't know. I would say awareness of some things is a fundamental ingredient of consciousness. Awareness of yourself and your place in the world and your relationship with the environment. I would say this is a fundamental ingredient of consciousness, or I perceive it as it is as a fundamental ingredient.
Okay.
Awareness, you can be aware of some things, but maybe not fully conscious.
Mm-hmm. Yep. Okay. Do you think that a sort of a theory of everything or whatever for this name, will it be able to achieve an explanation of the emergence of what will consciousness be defined as?
No.
Okay. So,
So a theory of everything would be a set of rules
mhm,
to which all the arrows of
mhm,
all Weinberg's arrows of explanations
yep.
point to. But then consciousness is a biological phenomenon.
Okay.
Consciousness is something that evolved biologically because it was convenient in some life forms, including humans.
Mhm.
And it's a very complicated process that would be it would be very naive to try to explain that with the fundamental laws of the universe, just like we do not use quantum chromodynamics to explain chemistry. And not just quantum chromodynamics, but
Mhm.
you know what I mean. It's the same thing.
Okay.
So consciousness is a biological process. That's
Okay.
it.
Do you think we will ever find a biological explanation or an explanation within neuroscience
Could be.
for why?
Could be. Yeah, we might have breakthroughs in neuroscience and understand exactly, I don't know, what kind of link in the brain leads to what kind of function.
Okay.
So different functions. Maybe one of these could be like the ability of being conscious or aware. Could be.
Mhm.
We may be able one day to take a brain and scan it and take a bunch of data and then have an algorithm that from that data tells you whether that brain is conscious or not. I think it could be possible.
Okay. Could it be the case that within the brain, the neural activity, there are some processes within the neural activity which defies our understanding of the laws of physics?
No, why? I really don't think there's anything magical going on in the brain.
Okay.
I mean, we know what the brain is made of.
Okay.
It's just cells
Mm-hmm.
that exchange electric signals.
Okay.
I'm not an expert in biology, but like we know what's going on in the brain.
Uh-huh.
Why would you like the emergent phenomena that come out of it are prodigious?
Exactly.
But that's I mean, it's not a surprise that from very complicated complex systems like the brain, you can have emergent phenomena.
Okay.
So I really don't think there's anything magical about it. It's just yeah, biology.
Okay. Do you think that the fact that okay, we have basically no idea, let's say scientifically, of what this thing we call consciousness is? We don't really have a theory saying consciousness is this. If you read 50 books of 50 different neuroscientists or psychologists, they will give you 50 different definitions of consciousness. Whereas for physics, we had some great unifications, and we got to be able to explain far-reaching phenomena, a whole wide range of phenomena. Why do you think is the case that we are such behind in understanding the brain and the phenomena of consciousness compared to physical processes as deep far in the cosmos inside the black hole until at the very center, which is the singularity? Um, why this sort of big discrepancy?
I think it's because physics is easier.
Okay. Okay.
Like a black hole is a remarkably simple object. There's just about a few equations you have to
Okay.
solve. While to understand a brain, oh my god, there are
Yeah.
so many neurons that interact in such a complicated way, and they can be in so different states, like many different states. That it's a complex system. So of course it's harder to understand. Like while many physical scenarios of interest are actually quite clean and simple.
Okay. Um, According to a more scientific view, people might say that there exists no such a thing as free will. Do you experience free will, or what do you think your free will is, or do you believe it is just an illusion encoded in the initial conditions of the universe?
So of course the impression that we all have is that we have free will,
Mhm.
and for practical purposes that's all that matters.
Okay.
Now, if I want to be consistent with my interpretation of quantum mechanics,
Okay.
then I have to tell you that free will might actually be an illusion,
Okay.
because
Why?
I don't know, if you believe that the evolution in time of the wave function of the universe is unitary, then there's no space for indeterminism.
Okay.
But it doesn't really matter.
Why?
How would it change my life?
I think more awareness of your conscious state and of your, or let's say, better consciousness, more conscious about your awareness state, in the light of being able to make decisions to change, yeah, the future, the things of events.
I don't think understanding quantum mechanics changes my my perception of free will at all.
Okay.
I think it's a completely separate issue.
Okay. Do you think could there be a connection between Gödel incompleteness theorem and our limited understanding or limited comprehension of nature?
Yes, but not currently.
Okay.
It could be that, the ultimate mathematical structure of the universe does suffer from this kind of limitation, but I wouldn't say it applies to our current state. We have so many things we don't know, so many things to discover, that I don't think it's a useful question to ask right now.
Okay.
Ultimately, it could be. It depends on the ultimate mathematical structure of the universe. Nobody knows what that is. So, yeah, Gödel's incompleteness theorems might apply to that.
Okay. When you think about the universe, not only mathematically, or maybe even mathematically, do you feel small, or do you still feel relevant because you know that you matter only to your scale? Your life is significant only to the scales.
So, yeah, when I think about the universe, I do not think in anthropic ways.
Okay.
So I do not need to feel big or small when I think about the universe.
Okay.
I am irrelevant for the universe.
Okay.
Okay. Then in everyday life, I don't know, I try to give the right importance to myself, not too much, not too little.
Of course.
But I feel like that's a separate thing from my relationship with the universe.
Okay. How would you describe your relationship with the universe?
Just a lot of curiosity.
Okay.
I feel like I'm at the window and I want to see what's out there. I want to understand what's going on and why.
Okay. How can the James Webb James Webb Space Telescope, revolutionize your field of research?
My field? Oh my God, I don't know. Yeah, what it can do, I guess, is shed light on galaxy formation,
Mm-hmm.
uh, which in turn depends on the content of the universe, when the universe was pretty young. So dark matter and so on. So maybe, astrophysical observations from those ages can tell us something about the content of the universe. Yeah, that's maybe the most relevant thing you can do.
Okay.
But I think the James Webb is more relevant for true astrophysicists. So, like, it can do a bunch of stuff for planetary science, for example, right?
Okay.
Right.
How would you feel if the James Webb Space Telescope or any other telescope would unveil, um, would reveal that there are other life forms in the universe?
So I don't think the James Webb can do that. The most it can do is, for example, to analyze the atmosphere of a planet and tell us, okay, it contains most likely this chemical substance. And then we might link that chemical substance to life processes.
Okay.
and deem it, less likely that it's produced by other natural processes. So I don't think the James Webb can give us direct evidence
Okay.
of extraterrestrial life.
Mhm.
That being said, it would be extremely exciting. It's of course like finding life elsewhere. It has always been one of the biggest, questions and sources of curiosity for humankind in exploring the universe. So I would be extremely excited
Mhm.
to learn that.
If you have to bet all your money
Yeah.
on whether or not there is other, firstly, simple life
Yes.
in the universe, and second of all, whether there is intelligent life.
Yes and yes.
Okay. All right. Without thinking about it. Why is it that? Is it because of the bit of the grandness of the universe, or anything else?
Well, the only case we know, life on Earth,
Mhm.
is based on some, chemical substances that are quite common in the universe.
Okay.
So it's totally reasonable that the same mechanisms could get started somewhere else. It looks like you just need the right elements and the right environment. It's not that hard, especially considering that life on Earth appeared like immediately after the formation of the Earth. So the fact that life exists elsewhere seems extremely likely to me. Now, intelligent life, that's a bit harder, even just for the fact that on Earth, apparently it took life 4.5 billion years to become intelligent. It could be that some species in the past was intelligent and then got extinct, and we don't know, but still, life was much simpler based on the fossil record a few billion years ago. So it looks like becoming intelligent is a harder process, or it takes a longer time at least.
Okay.
So that's harder probably to get intelligent. But what makes me think it's likely that it happened elsewhere as well is that it seems like it satisfies, like it's evolutionary convenient in some cases,
Okay.
like for our ancestors, for apes, and also for other big animals. There are many animals that are very intelligent.
Mhm.
It was very evolutionary convenient to be intelligent, and so you just need the right evolutionary driving force to develop intelligence. And I mean, if life exists elsewhere on other planets in other galaxies, most likely it follows biological evolution, like on Earth, and so that's how you could develop intelligence.
What is the most beautiful idea about the universe?
Beautiful idea about the universe in what sense?
The most beautiful concept about the cosmos, or physics, or anything?
Uh, I don't know. Maybe I could say um, the fact that it's fascinating. Like it could have been boring.
Sure.
It could have been that you looked up and there was nothing, and instead it seems so rich and interesting, and it looks like it contains so crazy things in it, like black holes and other galaxies, and the universe expands. Like it seems like it's full of
Surprises.
surprises. Yeah, maybe that's the most beautiful thing about the universe for me. I
Okay.
don't know. What is that for you?
I would agree with. I would probably say the richness of information that you can rip out of it. If you think about all the things that you can possibly know and describe in a universe, is pretty astounding. Uh, but probably, if I have to be probably more let's say, spontaneous, I would say the fact that among pretty simple physical processes, as you said, physics is simple. There arise, there arose a process which is our inner voice, which is able of a regression to the infinite, which means that if I now myself think the set of my thought is my consciousness, now the thought of me thinking about the set of my thought is another thought in my consciousness. And so it is basically like making one step forward behind me every time and looking me from every time a third perspective. And I can do this infinitely many times.
Yeah, I do agree that it's cute or interesting that the laws of nature do allow for physical objects like brains of some animals that are capable of this kind of complex thoughts. It's quite interesting. It means that the universe, like the laws of the universe, even though they are simple, they produce a very rich dynamics.
Okay, thank you for this conversation, Jim.
Thank you.
This was a conversation with Jimmy Tomaselli. Thanks for being with us. Thanks for listening. I hope you have enjoyed it. This was Back to the Stone Age.